Welcome back to the class on a HVDC transmission system. In this lecture, we are going to discuss about the effect of finite smoothing reactor in a DC. HVDC system is consisting of sending end as well as a receiving end stations. At sending end, the AC voltage will be converted to DC voltage. The DC voltage consisting of some amount of ripple. To decrease the ripple in a DC link current, we are keeping a one reactor. The reactor is nothing but a smoothing reactor. How do you select the smoothing reactor so that the ripples in a DC link current will be decreased? That we are going to see in this lecture. This is the converter, that may be the 6 pulse converter or 12 pulse converter. The output voltage of this converter is Vd of T. This is smoothing reactor. After the smoothing reactor, here we are assuming that constant voltage is there, that is the Vd. Theoretically, we are assuming that the DC link current is the constant. That is possible only if this smoothing reactor is infinite. But practically, we don't have an infinity reactor. The finite value of the reactor we are keeping here, so that the ripples in a DC current will be adjusted. The average DC current is more than the minimum value, such that the DC link current is the constant. Now the expression for the Vd of T, nothing but this is Vd of T. Vd of T equal to Em cos omega T, where omega T is greater than the minus pi by P plus alpha and less than the pi by P plus alpha, where P is nothing but a pulse number. Suppose here if we take the 6 pulse converter, then P value becomes a 6. If we take the 12 pulse converter, then the P value becomes a 12. We can find the average output voltage Vd, that is equal to integral from minus pi by P plus alpha to pi by P plus alpha Vd of T d omega T. In place of Vd of T, substitute the one equation and find the value. Compute this integration, that is equal to pi by P Em sin pi by P into cos alpha, where Em is nothing but a maximum line voltage, where P is nothing but a pulse number. If we observe the Vd of T and Vd waveform at alpha equal to 0 and alpha equal to 15 degrees means this is the waveform for the Vd of T, nothing but output of the converter. The average value is nothing but a constant value. This black line is nothing but a constant line, that is Vd at alpha equal to 0. The minimum value of Id will be occurs at this point where Vd of T equal to Vt, nothing but this instant. But in this case, the valve will be on at this point, so the minimum value of the DC link current will be occurs after the firing of the valve. In case of a alpha equal to 0, if the alpha value is increases, the minimum value of the Id will be occurs at which the valve will be on, and it is given by Vd equal to Em cos of alpha bar plus pi by P. Alpha bar is nothing but it is the angle at which minimum Id will be occurs. Already we have equation 3. That equation we have to substitute here, simplify, then we are getting the tan alpha bar equal to pi by P minus cot pi by P. If P equal to 6, nothing but a 6 pulse converter, then alpha bar is equal to 10 degrees. If P equal to 12, then alpha bar equal to 5 degrees. Nothing but the minimum Id will be occurs at this angle for the 12 pulse converter and 6 pulse converter. Generally, the firing angle is more than this one. So definitely there is existing in a ripples in a Id that we can able to find out. The expression for the Id we can find out from the equivalent circuit what we have seen. Id equal to voltage across the inductor plus Id minimum integral alpha minus pi by P to omega T. We know the value for the Vd of T and Vd. This is the expression for the Vd of T. Now substitute the VD of t in this equation and find out the integration. We are getting the ID equal to this expression. ID equal to 1 by omega LD Em sin omega t minus Em sin alpha minus pi by p minus Vd into omega t minus alpha plus pi by p plus ID mu. This is the expression for the ID. But we know the average value of the DC current. ID equal to P by 2 pi integral alpha minus pi by p to alpha plus pi by p. Sorry, here minus, it is not minus, plus alpha plus pi by p id of t into dt. In place of id of t, you take this expression, you complete this integration, we are getting the final expression, we are getting the id, nothing but a average DC current, that is equal to p by 6 into vd naught divided by omega ld into 1 minus pi by p cot pi by p into sin alpha plus id mu. Suppose if the DC link current is come to the zero, it becomes a discontinuous. So to maintain the DC link current is continuous, then you have to make this minimum value of DC link current is more than the zero. So ID minimum is equal to 0. You get the above equation. ID minimum equal to P by 6 into Vd naught by omega Ld into 1 minus pi by 6 cot pi by P into sin alpha. This is the one factor which is multiplied in the remaining expression. This factor value, if the P equal to 6, then that value becomes a 0.0931. The P equal to 12, this factor value becomes a 0.0230. So thank you very much for watching this video.